Welcome to this course on convective heat transfer. This being the first module, we will give a brief introduction on convective heat transfer. We will talk about what are the important terms like the heat transfer coefficient, Prandtl number, so on and so forth. And the following modules will cover various aspects of convective heat transfer, as you would have seen in the primer's 3-minute video. We would then have some application lectures. We would talk about special topics like boiling heat transfer. We would talk about applications like design of heat transfer equipment, so on and so forth. So, in this module, we will basically give a feel for what is convective heat transfer and why is it so important. So, as engineers, right from why engineers, as students of science, we would have been told that there are 3 modes of heat transfer, namely conduction, convection and radiation. Conduction, convection and radiation. This is 1, 2 and 3. And we would have been given definitions for this. Conduction is what happens because of molecular vibration. Radiation does not require a medium energy transport because of in the form of electromagnetic waves. Convective is where both molecular motion as well as bulk fluid transport. Molecular motion as well as bulk transport. This is what would have been the definition, and examples of this would be you have a spoon which is placed in a hot liquid. After some time the tip of the spoon also starts to become hot. This is a classic example given for conduction. Radiation heat transfer is how energy is coming from the sun to the earth. Convective heat transfer, various mechanisms would have been told to us, where how water is getting heated up and coming from a hot region to a cold region, how water is boiling for when you are trying to make tea. You have you are supplying heat at the bottom, but the water eventually at the top also becomes hot, so on and so forth. So, there are various real life applications where you see convective heat transfer. It could be a very simple application like boiling water for tea. It involves both single phase as well as two phase heat transfers. Single phase, I mean we have only one fluid which is there. Single phase, one fluid would be the water in its liquid phase. You can have water and oil in a situation that would be two fluid, and if they are both in liquid phase, it would be two fluid single phase. So, in this course we are going to talk of primarily single phase convection. We are going to talk a little about two phase, where our two phase refers to boiling heat transfer. We would also have couple of lectures on condensation heat transfer. These are both liquid plus vapor phase, liquid plus vapor phase situations. Both these studies would be for single fluid, single component, single component, single phase. That does not mean we cannot do it for multi component, we can do it. The physics would be similar, except that you have to account for different properties of the fluids which are together. So, you can have a mixture of refrigerants which would be there, which is going to be used in many air conditioning equipment, so on and so forth, where they could be carrying away heat from the location which needs to be cooled. So, you can have multi-component single phase, multi-component two phase, so on and so forth. You can have solid, liquid and gas existing. So, the point being, you can have various situations where convective heat transfer is existing. Convective heat transfer is basically you have flow. If this is a pipe you are talking about, you have flow, energy transfer because of flow and because the molecules of the fluid are going to also interact with each other. So, molecular interaction, transport, plus bulk fluid motion. Bulk means the entire fluid is moving. Bulk motion of fluid. These two together form what we call as the convective heat transfer. Okay. So, the important law which governs this convective heat transfer is this well known Newton's law of cooling. Newton's law of cooling is Q double prime is equal to H delta T. The Q double prime refers to Q divided by A. Q is total heat transfer rate, what you supply by means of an electric heater, this is in watts. This is the surface area through which heat transfer is occurring. Surface area through which heat transfer occurs. This is called as heat flux, watt per meter square. So, area in meter square, total heat transfer rate is in watt. Why rate? Joule per second. That is why we call it as a rate, heat transfer rate, energy transfer rate. Watt per meter squared is the SI unit for heat flux. This heat flux is equal to H into delta T, which is T wall minus T fluid. We will have different definitions for this. This could be T infinity in case of external flow. This could be T bulk mean in case of internal flow. This could be T sat in case of boiling or condensation. The point being, you are talking of a temperature difference. T infinity is free stream temperature, T bulk mean is bulk mean temperature, Tm bulk mean average. Free stream temperature, this is saturation temperature at a given pressure. So, the point being, you need to have a driving temperature difference. So, this is your T wall, this could be the T fluid. This T fluid could be T infinity in case of external flow, could be T bulk mean or T sat, depending on the problem in hand. So, for convective heat transfer to occur, you need to have temperature difference, and this is your wall Tw. So, if I have an external flow, so this seamlessly brings us to classification of convection. Classification, there are various types of classifications of possible. The first one based on the way or the geometry how it is happening. So, it is called external flow or internal flow. There are two types. External flow is flow over a surface, Internal flow is flow within a confined geometry. This could be a pipe, this could be an open channel flow like this. Whatever be it, you have a wall, you have a confined geometry through which the flow is happening. External flow is flow over a surface, flow around a cylinder where the fluid is flowing around a solid surface. This is a solid, this is a solid surface, flow over an aircraft. Okay. So, it is as if this is the flow which is happening. So, external flow you see in various real life applications. You have these transmission wires which are there. It's nothing but flow over a small cylinder. This is your transmission wire, and you have air flowing over it at all points of time, taking away the heat that is being generated by the current. You have various sport ball like golf ball, cricket ball, etc., over which flow is going to happen. These can also have heat transfer situations. So I have a heated cylinder which needs to be cooled. You supply cold fluid over it, it's going to get cooled. You have a heat exchanger which could just be a solid surface, your electric heater, hot plate, what you call. You keep a vessel of water over it, it is confining the sink into which the heat is going to go. Apart from that, if you just turn on the hot plate and you don't place any vessel over it, the heat is just going to get removed by the cold air which is over the surface. Internal flow through a pipe. So you have heat exchangers where you have one hot fluid, a cold fluid, which are either going to be in contact with each other, mixing, or which are in two separate pipes and heat is transferred across the wall. You have your storage water heater through which heat is supplied by electric current, and then you bring out cold water. You have two mixing streams which is going to give you one hot stream and a cold stream, giving you an intermediate temperature stream. This is all internal flow. In all these cases, heat transfer is occurring. So external flow, as you would have seen in fluid mechanics, we have what we call as a free stream velocity, and you have a free stream temperature, U infinity, T infinity. This U infinity and T infinity are taken as constant. This is free stream velocity, U infinity, free stream temperature, T infinity. When it flows, when there is a flow over a heated surface, you are going to form what we call as a boundary layer. We have seen what hydrodynamic boundary layer is. It is given by the symbol delta. This is my x coordinate, this is my y coordinate, and this is U infinity, T infinity. In fluid mechanics, we have seen this is the velocity profile. This is U of x comma y, U infinity here throughout. U of x comma y is the boundary layer velocity profile. What it means is that the velocity is 0 at the wall, goes to 99% of the free stream velocity, and you join these points where that 99% of free stream velocity occurs. That locus of points is called as the hydrodynamic boundary layer. Hydrodynamic boundary layer, velocity boundary layer as you call it, hydrodynamic or velocity boundary layer. It is given by a symbol delta. Within parenthesis x means it's a function of x or the flow direction. Okay. So boundary layer is a region where the flow field is separated into two parts. This is the inviscid part. Inviscid, this is the viscous part. By that I mean inside this region I have the effect of viscosity, which is important. Outside this region I don't need the effect of viscosity to be taken into account. By that I mean the viscous contribution is much smaller compared to the inertial and the pressure contribution. It does not mean that viscosity goes to 0. This is something which students do not understand. Inviscid approximation. Inviscid approximation, potential flow that you have studied in fluid mechanics, refers to an ideal situation. Ideal fluid flow, potential flow refers to a situation where all this behavior because of viscosity is not there. There is no effect of viscosity, which is important. Does not mean viscosity is 0. Viscous effects are negligible in comparison with the pressure and the inertial effect. That is what you need to emphasize here. Okay. So free stream velocity is like this. Just as you had a hydrodynamic boundary layer, because of the fact that you had a no slip condition at the wall. This is called as the no slip condition at the wall. That means u at the wall at y equal to 0 for stationary plate. There is no relative velocity between the plate and the first layer of fluid attached, which is in contact with the plate. Similarly, thermal no slip condition refers to the fact that for heat transfer to occur, T wall should be unequal to T infinity. Definitely you need to have a temperature difference for any heat transfer to occur. So, if T wall is greater than T infinity, heat will flow from the plate to the fluid is going to get hotter. The fluid is going to get hotter, very good. How are we going to see how the temperature distribution is like? So, the fluid will have the same temperature as the wall here. At a next location, this is showing by exaggeration, I would be here, smaller value, smaller value, smaller value, smaller value. Finally, I would reach a situation where the fluid temperature is virtually the same as the free stream temperature. This situation leads us to the understanding of the concept of a thermal boundary layer. This is your delta T of x, thermal boundary layer. This was velocity boundary layer, this is the thermal boundary layer. What is this definition? Is, remember one thing, unlike velocity, unlike the hydrodynamics, the heat transfer part is a little bit, wee bit complex. Hydrodynamics, fluid mechanics part has its own complexity because you deal with vector equations. Energy is that way good, you deal with scalar equations, but the problem being that you have, what are the two variables here in hydrodynamics? Let us just write them down. You have u of x comma y, local velocities, and u infinity, only these two in hydrodynamics. Whereas in case of heat transfer, this is hydrodynamics or fluid mechanics. In case of heat transfer, I have T infinity, I have T wall, and I have T local temperature. Fluid temperature at every point here is T of x comma y. Is this the same? Is it going to remain constant? No. I am going to have T of x comma y at the wall equal to T wall, progressively decreases. So, the effect of the presence of the heated wall is felt lesser and lesser as I move away from the wall, and the locus of the point here, what was your delta defined as in hydrodynamics? Delta refers to a situation where u by u infinity is 0.99, delta definition. This is your definition of delta, correct? So, you have u infinity, u local, here you have three quantities in heat transfer. What is the definition here? T minus T wall minus T infinity is the maximum temperature difference, correct? This should be 0.99 or 0.1. So, the T wall minus T infinity is the maximum, T local minus T infinity is 0.01, which if you translate this, it would come out to be 99%. So, this is going to be 99% of, so you would come almost equal to the bulk fluid temperature, and this is your local temperature distribution T of x comma y, and this point onwards the fluid temperature is only T infinity. What it means is that the fluid does not see the effect of the wall. If I am a fluid particle here versus a fluid particle here, A and B, fluid particle B would have a temperature greater than T infinity, lower than T wall, because it is inside this so called boundary layer. Fluid particle at location A would not know that there is a wall which is hot, and therefore the temperature would be equal to T infinity. This boundary layer delta T is called as a thermal boundary layer. This is called as a thermal boundary layer. Delta is the velocity boundary layer. Immediately you will ask me, what is the relationship between delta and delta T, which one is bigger, which one is smaller, so on and so forth. We will also see that hydrodynamic boundary layer and thermal boundary layer. It is normally told, or students remember this as delta by delta T is equal to PR to the power n. So, there is this non-dimensional number called Prandtl number. We have to come to all those definitions. One non-dimensional number that you saw in fluid mechanics is the so-called Reynolds number. For external flow, this is rho u infinity x by mu, which is R e subscript x. Remember, whatever is this, that is the same thing. For internal flow, this is external flow. For internal flow, you have RED is equal to rho u bulk mean d over mu. This is for internal flow. Now, we have not even drawn a single diagram for internal flow. What is internal flow? I said in internal flow, you have flow which is confined. This is internal flow. Flow which is confined. The flow is coming with a velocity u infinity. Very good. You have seen this in fluid mechanics. T infinity is the temperature. This is T wall. The moment it comes into the flow, into the pipe, it has to adjust to the fact that there is a solid wall which is surrounding it. Because there is a solid wall which is surrounding it, we will have a boundary layer which is formed. These boundary layer in 3 dimensions will merge at some location, which we end up calling as the entrance length, entry length or entrance length, hydrodynamic entrance length. And beyond this, we call the flow as fully developed. Mathematically, we said du by dz equal to 0. This is your r direction, this is your z direction. Okay. And we defined a velocity profile which was something like this for a laminar flow, and this is u of r comma z. We also defined a bulk mean velocity in fluid mechanics, which is called as u bulk mean or average or bulk mean velocity. Right. This fully developed flow was very useful in defining several things. And in internal flow, if we write here hydrodynamics, we have u of r comma z, you have u infinity, only 2 quantities, correct. In internal flow heat transfer, you have, let me draw the same thing. If I have T wall greater than T infinity, so heat is flowing into the fluid. This is my center line. Fluid is coming in at T infinity. A thermal boundary layer is formed like this, somewhere like this, and just as you had the temperature profile, please visualize, ask the students to visualize that this profile that we drew for external flow temperature profile would be similar here. You would have wall temperature greater T fluid. I am writing it as T fluid because you are having heat transfer, T wall is greater than T infinity. So, the fluid is going to get hotter as it flows along the direction. This is your R, this is my Z. I would have a temperature profile which looks like this and vertical here. What does this mean? This region beyond the thermal boundary layer, this is my delta T of x, does not know the presence of the wall, and because it doesn't know the presence of the wall, you see a vertical line. This is T wall, which is going to be a function of z. So T wall at z1. At the next location, I would have T wall at z2. Because the fluid is getting heated, T wall at z2 greater than T wall at z1. Am I right? And the region where the fluid is still at T infinity is very, very small. This region where the fluid is at T infinity, this is the region where fluid is still at T infinity, this is the region where fluid is at T infinity. It doesn't know that there is a wall. Once I come to this portion where the boundary layers have merged, there is no more region with T infinity. All I see is T wall at Z3 and no location of T infinity. Okay, the temperature profile is symmetric. So what are the three things that I have here? You have T wall, you have T infinity, you also have T local, T of r comma z. And when you have T of r comma z, just as you defined a u bulk mean velocity, using these we are going to define a T bulk mean temperature. So external flow, I will go back to this slide. External flow here had T infinity, had T wall. External flow had u infinity and u local. Here external flow we have T infinity, T local. Internal flow will have this additional quantity called bulk mean temperature, or mixing cup temperature as books call it, which needs to be defined. Our average temperature, water at 25 degree flows through a pipe or with a velocity 2 meter per second. That 2 meter per second is an average velocity. That 25 degrees centigrade is the average or bulk mean temperature. Both these numbers are something which you and I are very familiar with. These are what you and I as an engineer would need to use. Profiles, temperature distribution, velocity distribution are all needed in order to define quantities like wall shear stress, which is nothing but mu du by dy at wall. Similarly, we have what is called as the heat transfer coefficient, which is going to be defined as minus k dt by dy at the wall divided by some delta T reference. So this definition is analogous to what you had in fluid mechanics for wall shear stress, mu du by dy, k dt by dy. Okay. So for defining these things, you need u of r comma z, u of x comma y, t of r comma z or t of x comma y. As engineers, you would need u bulk mean, t bulk mean, where these represent the average values of the temperature, average values of the velocities that would be useful in determining several engineering quantities which can be directly used. These are more for distributions, so on and so forth. These are what a plumber you would say, I need a flow rate of so much. So you tell him if this is 1 inch diameter pipe, this should be the velocity. Those are gross quantities. These are more engineering quantities. In the next module, we will continue with the introduction, give the definition of Prandtl number, give the definition of local and average heat transfer coefficient, and end the classification. Thank you.